Hi, everyone, and welcome to this episode. If you're here, you're likely looking to find some information about specific heat capacity, which is one of the first topics that you will typically study in a unit on thermodynamics or thermochemistry. And so, what is specific heat capacity? Well, specific heat capacity, which we use the letter C for, capital C, is the amount of heat required to raise the temperature of 1 gram of a substance 1 degree Celsius. Okay, and I have a table of numbers here. This is a very small table. You can find giant tables of these in your textbook or on the internet or whatever. But I also have three samples of aluminum, copper, and lead. And they're not 1 gram, but let's pretend they are. Let's say I had a gram of a bunch of different substances sitting here in front of me, and they're at the same temperature, and I wanted to raise them all 1 degree. So 1 gram, 1 degree. Each one of these would actually absorb a different number of joules. They also have different densities too, but a different number of joules as they went from one temperature to 1 degree above that temperature. So each substance is unique and it has its own unique specific heat capacity. And it's given in units of joules per gram per degree. That's very important. And you can see, like, for example, gold is very low, whereas water is very high. And and these numbers, like I said, you can get on a chart. I wanted to show you one thing. This is a screenshot from an app that I have on my phone. And what it does is it's color coded the ranges of specific heat capacities, again in joules per gram degree. And if you look at it, you can maybe check out and see a pattern here where the highest heat capacities are up here at the top of the periodic table. And as you move toward the bottom of the periodic table, you get into the purples. And I think that's kind of a cool little pattern. And I actually learned something this week as I was doing some research, and I learned that that pattern was actually studied, and it's was put forth in something called the Dulong-Petit law. And what it basically says, in general, is that the heavier the element in its molar mass, the smaller its heat capacity. Smaller the number of joules it takes to get up 1 degree Celsius. Another way to say that is that its heat capacity times its molar mass tends to be fairly constant for a lot of elements. It usually is equal to about 3 times the ideal gas constant, 8.315, or around 25. So if you take the molar mass of an element multiplied by its heat capacity, you often will get a number somewhere in the mid 20s, which is really kind of cool. I didn't know that until this week. Okay, but if we're going to do some calculations with it, we need to have some direction. And I'm going to start with some easier problems, and in later videos work toward more complicated ones with different things going on. But this is the basic building block that you'll need to know. This Q equals Cm delta T. And there are a couple of variations. Depending on who you talk to, they might use slightly different symbols or different order, and that's okay. But it's the multiplying of three different factors. Q, which is the quantity of heat transferred, Q for obvious reasons, right? And that's going to be equal to the heat capacity, which you are either solving for or you're finding it on a chart somewhere. I always tell my students, don't memorize those because it's a lot. Times the mass, so this is joules per gram, but if we multiply by the grams that we have, and then also by the temperature change that it's going through, maybe it's not going 1 degrees, maybe it's going 50 degrees or 100 or whatever. And if we multiply those three together, we will get an answer that's in joules for the total amount of heat absorbed or lost by a substance. Okay? And let's start in with a quick example. And I'll show you the example first, and I'm going to show you a strategy I'm going to try to teach you as well. Example 1. How much heat will a 250-gram sample of water absorb when it's heated from 21 to 100? Now, you're going to see in this kind of a unit, you're going to see a lot of word problems, and there's lots of numbers in them and things like that. And maybe this will help. I always teach my students to try to come up with a strategy. And I teach them a series of questions to ask. When you're looking at a problem, ask yourself, is there a temperature change? And in this case, there was. But if there is, ask yourself again, is it just one substance changing temperature or two substances changing temperature? If it's just one, we have one Cm delta T. But if it's two, and we'll get to those, you actually have to have a Cm delta T term for both substances. And we're going to set that equal to 0. Later on, We're going to talk about phase changes like melting, freezing, boiling, etc. And that gets its own little version. And then sometimes there's both, where something heats up to its melting point and then melts, and you have to kind of figure out the total of those. And we'll get to those. But right now, I will repeat that. Let's go back to our question. How much heat will a 250-gram sample of water absorb when it's heated from 20? So this is a one sample. I only have one substance, water, and it does have a temperature change. So I'm just going to go ahead and write my formula. And a quick note, whenever you do delta T's, you should always do final minus initial. The delta T is the change in temperature. Final minus initial will always give you the correct sign of your answer, negative or positive. If the answer is negative, that means it's losing heat. If it's positive, it's gaining heat. So it's just a directional negative sign. So always a good idea to write down the formula you're using. Now the heat capacity of water from the chart that I just showed you is 4.184 joules per gram degrees Celsius. That's how many joules water gains for every gram for every degree. And that's a lot. It's actually one of the highest heat capacities ever, because of the fact that water does a lot of hydrogen bonding, and it's hard to like break those bonds and get those molecules to move around faster at a higher temperature. So I'm going to put in my mass, and again, final, which is 100, sorry about that, minus the initial at 21 degrees Celsius. And if I multiply all of those through, I'm getting an answer of 82,634. We'll adjust that in just a second. And what's the unit? Let's talk about units. So this is a compound unit, and the grams are going to cancel. The degrees Celsius will also cancel, and so we're left with joules. Now this is a big number, and I think I can do a little bit better with it because I have 4 digits here, but really only essentially 3 digits here. And so I want to just round my answer and just make it a little more generalized. So let's call it 82,600 joules. You may also want to put it in kilojoules at some point, so you're going to divide by 1,000, maybe 82.6 kilojoules. But that is your direct answer right there. Okay, so Q equals CM delta T. All right, your turn. So our first pause the video moment has one that looks like this. How much heat will a 100-gram sample of copper absorb as it's heated from 25 to 200? The specific heat capacity of copper, in case you didn't know that or have it memorized, it's 0.385 joules per gram degree. Take a moment, pause the video, and see if you can come up with a solution. All right, excellent. So when I did this problem, I got a solution of around 6,700 joules, or 6.7 kilojoules. Heat capacity goes in, the mass was 100, and we had 175 degrees of temperature change from 25 up to 200. So it came out to 6,700. So if you were able to get that, congratulations, you're doing wonderful, and we're off to a great start. Okay, we'll do a couple more quick examples. Example 3. A 50-gram sample of silver at 20 absorbs 1,200 joules when heated. What's its final temperature? And the specific heat capacity is given. So I'd ask myself, is there a temperature change? Well, yes. I don't know the final temperature, but I know it's changing. And there is only one substance. So I'm again using the same formula, Q equals CM, and I'll do T final minus T initial. Now, at this point, this one's different because I actually know what the Q is. Whenever you get your energy value in joules, put it in there. The heat capacity, 0.233 joules per gram degree. The mass is 50 grams. And I don't know what T final is, so I'm just going to leave it blank. That's going to be my variable. But I do know it starts at 20. 20.0, sorry about that. And then I have to do some math. I have to sort of collect these, divide them over to the other side, and then I'm going to get a number where I'll get something equals T final minus 20, and if I solve it correctly, T final ends up being 123 degrees Celsius. Okay, so there we have it. And if you got that, that's great. So let's try one more. similar one, so you get to practice your T finals. A 100-gram sample of water at 15 is placed on a hot plate where it absorbs 25,900 joules of heat. What's the final temperature of that water? And it's great that we have the power to predict that now that we know our heat capacity equation. Take a moment and see if you can do it if you'd like. Okay, and I got a final temperature of, when I did it, 76.9 degrees. This many joules went in. There's the heat capacity of water, mass of water, and then I'm solving for T final again. So again, I got a number equals T final minus 15. Add the 15 to both sides, and I get 76.9 degrees Celsius. So there you have it, a brief introduction to the simplest of heat capacity problems. In later videos, we will expand on that and look at more complicated situations. I hope they will help you, and we'll try to work on our strategy for problem solving these types of questions. In the meantime, if you have any suggestions of anything you'd like me to take a look at, you can send them to me. Otherwise, if you enjoy this video, feel free to subscribe or leave a comment in the comments. In the meantime, have a great day and happy solving.